Okay, study this phase. I want you to remember this phase for about 30 minutes. That's it. Just remember this phase for 30 minutes. It's important. Name, that's so much. But let's focus on the name anyway. What's his name? A lot of you guys are thinking his name is Philipp Lenard. Think again. No, that's not the way it is pronounced. It's Philipp Lenard. This guy is German. This guy is German. The reason why I want you to do this twofold. Number one, he wins the Nobel Prize for discovering something called the Photoelectric Effect in 1905. That's the main reason. Number two reason is because he's Einstein's professor. So he's Einstein's physics professor. He wins the Nobel Prize for something simple. It's a chance discovery. A lot of the people end up winning Nobel Prizes in early 1900s because of these chance discoveries. They're in the laboratory, they're goofing around, and all of a sudden they discover something real simple. All right. What exactly did he discover which is worth a Nobel Prize? Nothing much in reality. He discovered that by shining a light onto a metal surface, you can generate current. That's it. Bravo. All right. So shine a light onto a metal surface, and then you get electricity out of it. All right. So evidently, light is capable of liberating electrons from a metal surface. Who knew? All right. So that's a chance discovery. In 1902, he discovers it. A couple of weird things about it, though. The color of the light matters in terms of the amount of current that you generate. If you're using red, you get a certain amount of current. If you're using blue, oh my God, you get a lot more current than red. And then the intensity of the light is going to matter. You know what? The more intense the light is, the more current you get out of it. But the weird part of it is, if you're measuring the speed of the electrons ejected from a surface, intensity does not matter. You use dim red light, they're moving at a given speed. Bright red light, they're still moving at a given speed. So the maximum speed at which they're moving is identical. All right, dim, bright makes no difference. If you switch to blue, guess what? They're moving much faster. Dim blue, they're moving much faster. Bright blue, they're still moving much faster. But the maximum speed at which the electrons are moving is identical, whether it's dim or bright. Huge mystery. Huge mystery. Two mysteries. How is it that the light is liberating electrons from the surface? And why is that it depends on the frequency of the light and not the intensity? All right, so for this chance discovery, he's awarded the Nobel Prize in 1905. Then we got two mysteries. Light liberating electrons from a metal surface. The second mystery is why is it that the intensity doesn't matter in terms of how fast the charges are moving. Oh, this is one of the mysteries out of 4 or 5 that physicists don't know how to explain. There is a second mystery. It's been lingering over a century, otherwise known as the black body radiation. It's a simple phenomenon. When things are heated, they will glow at some point, as you all know. As it so happens, they will glow at red, and then you increase the temperature, there's going to be a shift in color towards the blue end. So initially, the color is going to be red, increase the temperature, everything is going to start shifting towards the blue end of the spectrum. So needless to say, the question is why? Why is it that there's a shift in color? Why is it that there is a shift in frequency from the red end of the spectrum to the blue end of the spectrum when you increase the temperature? So no one knew how to answer this question. The third one, you guys are under the impression, false impression that you know the answer. You don't. I just sold you a bridge on this one. Classical physics doesn't explain this question. Do you see this white light? It breaks into its color components, the red on top, the blue at the bottom. When I ask you why, and I think I might have asked you why on the test. If I haven't, I will definitely. Because if the frequency at the boundary is constant, the larger wavelengths will travel faster through the material, right? So the red is a larger wavelength than the blue. As a result, color red is going to travel faster through the material. This is more poetry than reality, as this happens. You're just describing what's going on without explaining why color red travels faster than blue. The reason why you don't know how to explain it because classical physics doesn't explain it. I didn't explain it. There's no explanation for it. The modern physics actually makes a really good attempt at it and provides an excellent explanation for it. All right, so at the turn of the century, 20th century, this is the third mystery that physicists don't know how to answer. So you got the regular light source, for prism, you end up getting a color spectrum. So you got the red on top and then violets at the bottom. And then something weird happens. You change your light source from a regular light source to hydrogen, and boom, you end up getting this color spectrum. You end up getting these 4 different colors. This is known as a line spectrum, color spectrum. And then you have these awesome colors. You got red, you get a combination of blue, green, and you have these 2 shades of violet. Where inside the hydrogen atom are these colors being generated? What's going on? What is the internal structure of an atom? So this becomes a question, once again, no one knows how to answer. No one knew how to answer this question for nearly 100 years. I'm not talking about somebody discovered it last week and we still don't have an answer. This is like, this was discovered in the early 1800s. And then this is the beginning of the 20th century. And still no answer, still no answer. Except this guy, who happens to be a mathematician, teaching at a nursing school. I imagine the life is really boring because they don't have internet, TV, or whatever. All right, and decided to play with this idea of the Huntington length spectrum. So he's just goofing around with it and looking for a pattern, a mathematical pattern. Eventually, he discovers a pattern, which is formulated in this format that you're looking at. All right, so F on the left is the frequency of the line that you're looking at. Frequency of red, it could be blue, green, or two shades of violet. All right, so C is the light speed. R is known as the Rydberg's constant. So whatever this is in front of the parentheses, this is a huge number. C is going to be 10 to the 8th. R is going to be 10 to the 7th. In reality, whatever this says, this number is 10 to the 13th. And somehow somebody decided to break it into two constants. And somebody decided to express it in terms of light speed. It's got to be Rydberg himself must have done it because Balmer is the one who came up with it. And then he breaks it into two portions, and the leftover is the Rydberg's constant. So I think Rydberg is the guy who just said, okay, this is too big of a number. Let me break it into two chunks. Okay, that's fine. There's no mystery here. Mystery is here. This n is the mystery. Evidently, n is an integer that you're looking at. The integer is a whole number. If it's 3, it's going to give you the frequency of red precisely. If it's 4, it's going to give you the frequency of combination of blue, green. And 4, 5, and 6 is going to give you two shades of violet. So 3 is going to give you red. 4 is going to give you the frequency of blue, green. 5 and 6 is going to give you two shades of violet. There you go. This was awesome. So the question is, what is n? Oh my God, what is n? It's an integer. Why does this formula work so well? And is a number larger than 2? If it's 3, 4, 5, and 6, you end up getting the frequencies of the spectral lines without you not. Precisely. So the mystery. The puzzle is not solved, the mystery deepens, because what is n? Where do we get the n from? What does that signify regarding the internal structure of the hydrogen? This guy, his name is Planck. It's not Planck, it's Planck. It's Planck, it's Planck. German. It's a hard A. Solves the problem regarding the black body radiation. Remember what the black body radiation is. When things are heated, they will glow in red at first. So as you increase the temperature, there's going to be a shift in color towards the blue end. People worked on it for nearly 100 years, and evidently, the solution was a simple mistake away. Just a math error, a bad assumption. And Planck was able to solve it. Who knew? All right, so he's trying to solve the problem. Evidently, he skipped a step, introduced a constant, thinking that the constant was going to cancel out or go to 0. It was supposed to integrate something if I forgot to do it. So it follows the algebra, and then boom, he was able to solve the problem. All right, so before talking about how he solved the problem, let's focus on what we're looking at. This is the intensity of the color that you're looking at. It could be red, blue, green, whatever. All right, when things are heated, they will glow, right? That's what that is. All right, so this is the peak intensity. This is the frequency. All right, so when you start to increase the temperature is going up. What's going on is the peak intensity is going to, the frequency of the peak intensity is going to shift from left to right, which means that the colors will shift from the red end of the spectrum towards the blue end. The only thing I want you to take a look at is this shape. It's a camel hump. All right, it looks like a camel hump. The humps are just moving in the forward direction. Increase the temperature, the peak intensity is going to shift from red towards the blue end. All right, just remember the shape. These are known as the black body radiation curves. That's what they are called. And Planck knew that he solved the problem because when he plotted his solution, he came up with a black body radiation curve at a given temperature. And when he plotted the data against it, the data that you're looking at, these dots, perfectly match the solution, the curve that the solution generated. That's it. All right. Except there's a slight catch, which came out of the way he was solving the problem, the step that he skipped, the constant that he introduced, which was supposed to either go to 0 or cancel out, which it didn't. Which it did not. It didn't cancel out. It didn't go to 0. It came damn close to going to 0. All right, so this constant is known as the Planck's constant. got 33 zeros before you hit the first number, right? With this constant in place, everything worked out. And what is the meaning? What the meaning of that is, assuming that the energy is quantized, assuming that the energy comes in small packages, assuming that the energy comes in small units, you can solve this problem as it so happens. All right, that's known as quantum mechanics. So assuming that the energy comes in small units, this problem can be solved. All right, so it seems real innocent. All right, this guy just stumbles onto something and he solves the problem. So what's the meaning of energy coming from in small chunks, small units? Oh, you know what we've been talking about, you know, when you drop a ball, potential energy turns into kinetic energy. It's a one continuous process. It just so happens it's not a one continuous process. It just happens in small steps. Except the step size is so small you don't notice it. All right, so evidently nature itself is not continuous. All right, so energy is not continuous. Energy just goes up or down in small chunks, small step sizes, small step sizes. That's the stuff that he discovered. In fact, these step sizes are so small. From our perspective, it looks continuous. When you drop a ball, what happens is potential energy continues to turn into kinetic energy. That's it. But in reality, it's happening in small units. For example, I'm drinking coffee here. It feels smooth on my tongue because it's so liquid. It's delicious. Despite the fact that it's made up of small chunks of particles called molecules. But I don't feel those individual molecules. I don't feel those individual chunks. At the level that I'm living, all right, it looks smooth, it tastes smooth to me. It's the same exact idea. It seems like a really innocent thing that he discovered. So if the energy is quantized, you know what? You can solve the black body radiation problem. All right, he solves the problem in 1899. This is cute. Move forward, and blah, blah, blah. And then I'm just looking at the history. 1900, finally, he publishes it. This is so cute. About a year later, he's sitting on it. No, he actually presents it in 1900 and publishes it in 1901. And then guess what? Wins the Nobel Prize in 1918. Okay, so when you're looking at information up like that, you end up missing a lot of the important details. Okay, so number one, everything that you're looking at verbatim is plagiarized. One thing I did is something most of you guys are really good at. Okay, so when you guys do it on the test, obviously you guys don't get a lot of points. When you guys are doing the conceptual section of the test, you're thinking, yeah, but the information should be correct. How do you know if it's correct? Obviously, you're clueless. That's the reason why. When you guys copy and paste, if something is written by a physicist, obviously I'm a physicist, your understanding of physics is not there. You copy it and paste it, and then you get duck points, like you get half a point for being able to copy and paste something. Because there's no way you can defend somebody else's work. You can just challenge me on it, say, hey, why did I lose points? I could just say, what is it that you wrote here? Just explain it, defend it. You won't be able to defend yourself. It's so sad. And I'm doing exactly the same thing to you guys. I go to my favorite source. I'm plagiarizing. My favorite source is Wikipedia. I just plagiarize the shit out of Wikipedia under the circumstances. Now that I said it, it's no longer plagiarism because now I'm giving him credit. On top of that, I'm telling you that I verbatim just copied everything. Did I change a single sentence? No word, absolutely not. Because I'm trying to make a point here. I go to Wikipedia only if I want to see an update or quick summary of something. All right, that's it. If I'm working on research, I want to see where the research is. These guys do a really good job. If there's a news item, if I want to get an accurate reporting on a news, once again, I go to Wikipedia. Guess what? I don't go to CNN. I don't go to ABC. I don't go to Fox. Just go to Wikipedia. You will find the same stuff there, except it's not going to be interpreted for you. It's kind of weird how things work out. So, for Max Planck, it's not Max Planck. It's Max Planck. The guy is German. All of a sudden, I'm looking at the dates, and then something is off. Something is off. Something is off. What's up? What's off is, number one, he solved the problem in 1899. He's sitting on it. And then finally, about a year later, he says, oh, it's about time. Let's just go forward and then just claim victory. And then he's still sitting on it. In 1901, he publishes it. In 1918, he wins the Nobel Prize. Oh, my God. I mean, Disney would have been proud of the way this is put together on Wikipedia. They're just so artificial and made up. All these details are missing. What I'm looking at is a major constipation here. 1899, that is it. 1900 presents it. And 1901, he finally publishes it. 2 years of hesitation. What the hell is going on? Einstein didn't have that problem. He's working on gravity problem. 1913, he just comes forward. He publishes it. He said, listen, I'm working on it. This is as far as I got. I'm stuck. I don't know where to go with it, but I'm going to keep working on it. He publishes it because he wants to claim priority. It's a major discovery. This guy solved the biggest problem in physics. People have been working on it for 100 years. You solve the problem. Don't sit on it. Just come forward. Claim victory. He's not doing it. He's sitting on it. Why? The reason why he's sitting on it because he's afraid that he's going to lose his job. What energy quantized means, guys, let me translate the English for you. Quantization of energy means, or the energy quantized means that light is a freaking particle. We've been discussing that. What's the nature of light? Wave. Every single experiment proves that the light is a wave. And all of a sudden, out of this math, he solves a problem. Now he's trying to figure out, because physics is not math. Now you have to interpret the meaning of what you came up with. The meaning of what he came up with is literally light must be a particle. How are you going to explain it to the world? He doesn't know. And you're thinking, oh, what's the big deal? People will understand. No, that's not how it is, guys. No one is going to understand that. This is a well-established physicist. And there's no way you can come forward and say, hey, listen, pal, assume that the light is a particle. I solved the problem. Black body radiation problem can be explained. The meaning of it is the light has frequency, right? Red has a frequency of whatever. So is blue, so is green, so is violet. So multiplying it by H means that you take the light and then turn it into a particle. You create a small packet of light. You end up creating a small chunk of light. All right, that's what it means. Energy gets quantized, which means that the light turns into a packet, which means that the light turns into a particle. So assuming that the light is a particle, boom, the problem is solved. Except you can't say that, because if he did, he's going to lose the respect of his colleagues. Potentially, he can lose his job. And the thing to understand is, guys, this is 100 years ago, 120 years ago. How many people do you think was working in physics? How many people do you think have PhDs in physics back then? I'll say probably about 1,000 people in the entirety of the world. And 1,000 might be an exaggeration. It was next to impossible to get these professorships back then. He was lucky enough to get one. Now he doesn't want to lose it. What would happen if he were to lose it? Guess what? He would not have a job. He would not have a job. Okay. I mean, if he's lucky, he'll be teaching high school or something. He doesn't want to take a chance. He just doesn't know how to explain how light could be a particle. Given the fact that every single experiment done up to that point proved that the light is a wave. It's not a particle. So the first thing he does is sits on the information for a while because he doesn't know how to explain it. Now he's tempted to actually claim victory over it. So he presents this stuff. He does what most of us are really good at in the physics community. Do a presentation, make it as mathematical as possible, because he's going to be able to follow the math. Not too many people can, believe it or not. Guys, you do hand-waving argument, you hide behind the math. In fact, the less the instructor knows about what's going on, the more mathematical it usually gets. Right? Because you can kill a lot of time just doing derivations, this and that. And then at the end of it, it says, oh, here's the final formula I came up with. Look, when you graph it, this is what you come up with. So you get the black body radiation curve. And then here, these are the data points. And they put the data points on top. And then boom, the problem is solved. And then you kind of put the emphasis on, you know what, there's this constant. It's a small number, obviously. It was supposed to go to 0, it stops going to 0. And it gives you something like that. He doesn't really explain it. People are impressed that he was able to solve the problem. And no one actually pays any more attention to it. Okay, you can get away with that presentation. It's smoke and mirrors at that point. Except publishing a paper is a lot more complicated, because you kind of have to write out your derivation step by step, explain your assumptions the way I asked you guys to explain your assumptions and your solutions, and provide explanations as to how it's supposed to be done. It gets complicated. So he doesn't quite know how to do it, because the experts are going to look at it and read it, and then you may or may not be able to get away with it. So there's some problems. And he spends about a year thinking about how he's going to do it, because this is what he needs to explain. This is the fundamental equation that comes out of it. Simply put, this frequency gets quantized. All right. So which means that this turns into an energy particle. All right. So red is going to carry a certain amount of energy. The blue is going to carry a certain amount of energy. Violet is going to carry a certain amount of energy. That's it. It's clear. This needs to be explained why. Eventually, after 2 years of thinking about it, he says, okay, I know what's going on here. Light is a wave, he said. But the way the light is processed by the atom is quantized. Like the way you drink water. You don't drink the entire ocean of water. You just do it 1 cup at a time. All right. In essence, you kind of quantize it. All right. You turn it into 1 chunk of water, 1 cup of water. It's the same idea. The way the energy is absorbed and re-emitted by the atom is quantized, not the light itself. The way the light is absorbed and emitted by the atom itself is quantized. Now he's fine. He said, okay, so it's good enough. So he publishes it. So people were impressed, obviously. People were impressed, but not to the extent that he was going to win the Nobel Prize for it. And then something else happens. He wins the Nobel Prize because of some weirdness in history. All right, so the weirdness is about to happen because somebody is going to enter into the arena. All right, so Philipp Lenard, 1902, chance discovery, light liberates electrons. All right, so frequency of light matters. If you're using red, electrons moving at a given speed, you will get a certain amount of current. If you're using blue, they're moving faster. Brightness of light doesn't matter, as it so happens. Dim red, bright red, electrons are still moving at the same speed. Dim blue, bright blue, electrons are moving faster, but they're still moving at the same speed. All right, so the mystery lingers. Anyway, so this is a big enough discovery, so he's awarded Nobel Prize in 1905. And 1905 is a weird year for Einstein because he's working on his PhD. And this is the year he publishes 5 papers, by the way. The first paper that he publishes is the proof of the existence of molecules. All right, I put a smile on my face because in the physics community at the time, and this is 1905, this is 1905, this is 115, 16 years ago, majority of physicists did not believe in the existence of atoms or molecules. It's highly questioned. It was the theory was suspect. Physicists did not believe in the existence of atoms and molecules. Most physicists didn't. They questioned it, and a lot of chemists did not believe in it either. They thought that it was just a mathematical construct, and that's it. They would not dare think that this stuff was real. In 1905. So Einstein, the first thing he did, by using actual experimental data for Brownian motion, whatever that is, we'll discuss it later. He proved the existence of molecules. That was first paper. And then the size of the molecules, he decided to turn that into his PhD dissertation, one of the easiest papers that he worked on. And the topic was fairly easy as far as he was concerned. In fact, it was so easy to follow that his research dissertation committee professors could follow it. I mean, Einstein was cocky. He didn't think very highly of his professors, so he decided to pick something that they would have a hard time disputing, and decided that he was going to just dumb it down enough so that these people could follow it. He didn't want to risk not getting his PhD. He wanted to find something which is easy enough and dumb enough. And he wanted to dumb it down as much as possible so these people could actually look at it and say, okay, so this guy's right. So his second paper was literally the size of the molecules. Not an imaginative thing, but it was a safe choice. The third paper that he was working on at the time was special relativity. That was his obsession. He'd been thinking about it for 10 years. Finally, he said, okay, I figured it out. Finally, I figured it out. If light moves at the light speed in my reference frame while I'm traveling at the light speed, if the same light travels at the light speed in your reference frame, so something has to happen to time, something has to happen to space, and that's it. That was the third paper. And all of a sudden, boom, 1905, his physics professor, Lenard, who wins the Nobel Prize. And Einstein goes, well, photoelectric effect. He finds out that's a photoelectric effect is a mystery. No one knows how to solve it. So why not solve it himself? I don't know how long it took him, maybe a day or two, maybe a week. It didn't take him that long. This was like one of the easiest papers that he published. He goes, assuming that the light is quantized, this is how it starts. Remember his postulate. Assuming that light is quantized, postulate 1, light is quantized. Then he noticed that this is a real easy problem to solve. All right, so the light is liberating electrons from the metal surface is because if light is quantized, this is the red color, all right? It's going to carry a certain amount of energy. So the electron is going to absorb this amount of energy. It's going to become energized, and then it's going to jump out of the metal. That's it. All right, so it's going to jump out. It's going to keep moving at a given speed. If it's blue, you know, the blue has a larger frequency, so it's going to carry more energy. As a result, the electrons liberated by blue will be moving faster. Guys, that's it. This is like a coffee shop discussion. All right, so obviously, light is energizing electrons. So you don't need to be a freaking genius to figure this out. I mean, it's not even rocket science. You're just sitting there. Look, the electrons are being energized by light. All right, the electrons liberated by red moving at a given speed, and the electrons liberated by blue moving faster. What do you think is happening? Blue has a larger frequency, so it carries more energy. That's it. All right, so it's a conceptual process. So once you figure that out, the rest is straightforward. Just sit down and then do the derivation, come up with some kind of mathematical expression. So high frequency light, in essence, is going to carry more energy. The low frequency light is going to carry less energy, right? So these energy packages are known as photons. So red is going to carry a certain amount of energy. And guess what? The violet is going to carry more energy. Now what happens? Well, you know, the electron that gets energized by violet is going to be moving faster than the one which is energized by red. All right, so this is the amount of energy that energizes the electron. So this is the amount of energy that's going to get absorbed by the electron, or the amount of energy that energizes the electron. Now, this is the amount of work that the electron needs to do in order to free itself from the metal. So this is the amount of energy that the electron takes in, and this is the amount of work that it needs to do, the energy that it needs to spend. And the difference is the kinetic energy of the electron. This is how fast the electron is making a getaway. This is the maximum speed at which the electron is moving. Okay, so it's like a jailbreak. All right, so this is the amount of food they eat, one bite at a time, in order to keep yourself healthy and alive. And you're digging a tunnel, so this is the amount of work that you need to do in order to dig a tunnel. And if you're still alive at the end of the digging process, if you still got energy left over, this is how fast you're going to do your getaway. Okay, I mean, it's straightforward. Of course, I didn't sit down and then, hey, just like a jailbreak or getaway. All right, this is about, there's 1 or 2 pages of derivation involved, but the end result is straightforward. Okay, so this is the photon of energy. This is the packet of energy that energizes the electron. All right, so if it's red, electrons are moving at a given speed. If it's blue, it's higher frequency, they're going to be moving faster. All right, so it's straightforward. Intensity is not going to matter. The only thing that matters is the color. Intensity is related to the number of photons, the energy packages that you have. So the intensity is related to the number of photons, or the energy packages that you have. It's more intense, fine, it's going to be able to liberate more electrons. Less intense, it's going to be able to liberate less electrons. But the maximum speed with which the electrons are going to be traveling is related to the frequency of the light. Dim red, bright red, doesn't matter. Maximum speed at which the electrons would be moving still will be the same.
And the evidence can still be seen today in the behavior of a gold leaf electroscope. When the electroscope is charged, the leaf rises and stays aloft until it's hit by a beam of ultraviolet light. An ordinary piece of glass transmits visible light, but it blocks the high-frequency ultraviolet light. When it's interposed, the electroscope doesn't discharge. But when the glass is removed, the leaf falls again. This proves that the ultraviolet light does the job, and it's called the photoelectric effect.
Okay, so you got a metal piece, you can charge it up negatively by touching it. All right, so this rod is negatively charged. As soon as you touch it to the metal surface, the charges are going to be free to move. They're going to get repelled onto the metal surface. And then obviously, when they're in metal, they're going to get repelled to the surface, right? So the surface of it is negatively charged. You got 2 metal pieces. Both of them are charged negatively. So you got a gold leaf and a metal piece here. So they will repel. All right, so they use an ultraviolet light source. Ultraviolet is going to be higher frequency than violet. So which means that it's going to be carrying high energy photons. And as soon as the high energy photons hit the electrons, obviously notice that the electrons are liberated from these metal pieces. As a result, the force of repulsion diminishes. That's what happened. Now what they're doing is, once again, they charge the metal pieces negatively, so they're repelled with respect to each other. Now he's using a glass barrier. One of the things that you need to know is the ultraviolet would not go through glass. All right, so when you put a glass piece, notice that there's no photoelectric effect. As soon as you remove glass, there's photoelectric effect. So the ultraviolet is going to be higher frequency than violet. As a result, the electrons are going to get stripped off or liberated much faster. All right, so this is what Lenard came up with. This is a simple enough experiment. And somehow this was a chance to discover. So Einstein solves the problem. He's all excited about it. All right, so he's working, he's done with the theory of special relativity. I think he already wrote it for publication. And then he gets this in the last second, photoelectric effect. And then he sends both papers for publication at the same time to this physics journal. Guess who is the editor-in-chief of the physics journal? It's Planck. So Planck gets a hold of the papers. Now he's trying to make a decision whether or not the papers are going to get published. He looked at the photoelectric effect first. And then, Einstein, he's just like, oh, assuming this, assuming that, the postulate one, postulate two. He's just postulating the hell out of everything. All right, so Einstein is like famous for, oh, based on these postulates, let's check to see what happens. His papers are always like that. Again, his papers are assuming that the light is a particle. Of course, the higher frequency light is going to carry more energy. Then you can explain the photoelectric effect. And then there's 2 pages of derivations, resulting with the formula that I showed you. Except Planck is very sensitive about that because evidently Einstein read Planck's paper and then using Planck's paper as a reference. And Planck doesn't like that because of that sort of interpretation, potential interpretation, he was reluctant publishing that paper in the first place. He doesn't want to draw attention to that. He doesn't believe that the light is a particle. He believes that the light, he already came to terms with light being a wave, the way it is absorbed and remitted, the process by the atom is quantized as far as he's concerned, not the light itself. And Einstein just comes out of nowhere and says, hey, assume that light is a particle. Forget about being a wave. Assume that it's a particle. We can solve this problem. There's no bullshitting. We can solve this problem. Except Planck is the judge on the execution on the circumstances. He doesn't agree with that interpretation. Looks at the math, looks at the solutions. He's impressed with it. Except, guess what, guys? The physics is not math. I don't care how elegant your mathematics or derivation is. Your assumptions matter. Quality of your solution is as good as the quality of your assumption. And the assumption that the light is a particle is a really bad one in the face of evidence. Because every single experiment done up to that point proves that the light is a wave. It's a transverse wave. Newton thought it was a particle. He was wrong. You can't just come forward as if this has not been debated. This has been debated for 200 years. He puts the paper aside. That paper is not going to get published. Bad assumption. It doesn't matter how good the math is. It's a bad assumption. It looks at the second paper. He's expecting the same sort of nonsense because once again, Einstein is postulating the hell out of everything. Oh, assuming that you're traveling at light speed, you get a mirror in your hand, you look into the mirror, and guess what? You see your reflection. So what gives? Blah, 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 blah. Number one, Planck didn't realize that there was a problem there with the Maxwell's equation. Number two, he's freaking impressed. That paper impresses the hell out of him. He looks at it, it's so counterintuitive. He's thinking about it, he can't find anything wrong with it. And then all of a sudden he's looking at a paper that's written clearly, written by someone who's above and beyond anybody else, like complete freaking genius. And then he takes a step back and says, wait a minute, he wants to publish that paper, but at the same time, he cannot publish that and not publish the other one. It just makes no sense because it's the same freak. He wrote both of them. He completely disagrees with Einstein's view that the light is a particle. And then he says, what the hell? What the hell? Just publish both of them. what's the going to happen? Who's going to read it? Who's going to understand it? Anyway, what the hell? I mean, just publish them both. What papers get published? Now he's curious about Einstein. At first, he thought that Einstein had a professorship somewhere, only to find out that this guy is actually, the year is like 2005. Finds out that Einstein is actually working in a patent office as a second-class clerk. And then now he wants to mentor him because Planck is well established. He starts looking for a professorship in German universities, prestigious German universities. I'm not talking about a community college level. I'm talking about real prestigious German universities for him. And then he's got his eye on the Prussian economy, which is almost like Harvard. And he's trying to sell Einstein. He apologizes on behalf of Einstein. He says, yes, this guy is young. He's like 26, 27. He believes that the light is a particle. All right, so if you overlook that little bit of thing, just hire him. You will not regret it. All right, because this guy is one of the best things in physics. And this is going to be a great investment on your behalf. Of course, Einstein gets his first professorship over at Prussian Academy. And then something weird happens. A local guy, Robert Millikan, when I say local guy, I mean local guy in the sense that local guy in Chicago, University of Chicago. Someone named Robert Millikan, one of the best experimental physicists of his day. For one of the reasons, gets a hold of Einstein's paper, and he decides to disprove Einstein because he feels that light is a wave, it's not a particle. And he also feels that he's good enough to prove Einstein wrong. So he starts setting up experiments over at the University of Chicago the first series of experiments that he conducts the first year, all of them prove Einstein right. But this guy's adamant. He figures that his experiments are not sophisticated enough. So it comes up with more sophisticated experiments the following year. Once again, every single experiment proves Einstein right. He says, no, these experiments are not sophisticated enough. So he spends the third year conducting experiments. Once again, the same result. And he's not going to give up. Only thing he knows is he could do better. He could do better because it takes only one experiment to disprove something. And he keeps at it. He comes up with more and more sophisticated experiments the fourth year. And once again, every single experiment proves Einstein right. And finally, he gives up 1917. In trying to disprove Einstein, he ends up proving Einstein right, meaning that the energy is quantized. And because he ends up proving Einstein's photoelectric effect correct, guess who wins the Nobel Prize in 1918? Planck does. In 1917 proves that the energy is quantized. In 1918, for discovering that the energy is quantized, Planck wins the Nobel Prize. The Planck apologized on behalf of Einstein, saying that Einstein wrongfully believes that the light is a particle. Ends up winning the Nobel Prize for assuming that the light is a particle and being able to solve the black body radiation problem. All right, so every single experiment he conducts ends up proving that the light is quantized. All right, so the Millikan, different metals, different work functions. This is the amount of work that the electron needs to do in order to liberate itself from the metal surface, and all of them have the same slope. Guess what, guys? The slope equals to the Planck's constant. What that means is the energy is quantized. And for proving Einstein right, he wins the Nobel Prize in 1923.
It was the perfect solution, and proved as such by Robert A. Millikan in his Chicago laboratory. When he measured the energies of electrons ejected from various metals by different frequencies of light, Millikan verified that while each metal has a different work function, Planck's constant has the same universal value for all of them. But this explanation of the photoelectric effect not only confirmed Planck's theory, it showed directly that bundles of energy already exist in the electromagnetic field. In other words, light comes in particles which are now called photons.
Wins the 1923 Nobel Prize for proving Einstein right. Einstein wins the Nobel Prize in 1922. Thanks to Robert Millikan, and thanks to Einstein and Robert Millikan, Planck wins the 1918 Nobel Prize. Okay, so here's a fun fact. Millikan went to his grave thinking that Einstein was wrong. He just could not come up with a sophisticated enough experiment to prove him wrong. All right, he was never convinced that Einstein was right. He always believed that the light was a ray. He just couldn't prove it somehow. And he could never come up with a sophisticated enough experiment. Planck went to his grave thinking that Einstein was wrong. Light was a wave, it's just the way it was processed by the atom was quantized. The way it is absorbed and re-emitted by the electron was quantized, which means that, because electron can only take a small chunk of it, that's what it means. So he was never convinced that the energy was quantized, or the light was quantized. He thought that was just complete nonsense. Einstein went to his grave thinking, what the hell did I do? Because he created this monster called the quantum theory. And all of a sudden, he introduces a probabilistic interpretation to quantum mechanics in 1918 for the reason, something that we'll discuss later. And then eventually, the probabilistic interpretation became the interpretation of modern physics, which he absolutely hated. The 1925 on, he tried to disprove the quantum theory for the rest of his life unsuccessfully. That didn't work out. So Millikan hated Einstein's photoelectric effect, his interpretation, obviously. Planck hated the basic assumption of the photoelectric effect. Millikan hated the conclusion of the photoelectric effect, as well as the basic assumption of it. And the guy that we started the lecture with, Philipp Lenard, absolutely and passionately hated Einstein, the man himself. Okay, so that's a little bit different. You can hate somebody's theory, but this guy passionately hated Einstein. Passionately. It's called professional jealousy. He discovered the photoelectric effect, just chance discovery. You flip a switch, the light is on. Thank you for giving me the Nobel Prize. All right, no explanation for it. It was a complete mystery, and his student came forward and explained it and completely revolutionized science, the physics. Einstein literally single-handedly turned physics upside down and revolutionized it. There was no competing with Einstein. And this guy could not stand it. How do we know that? It's simple. You're thinking, oh, he must have written a diary or no, guys, it was capable of doing much worse. It became an advisor to Hitler. He hated Einstein to an extent that he became advisor to Hitler. He started the Jewish physics, German physics phenomena. All these Jewish physicists end up losing their professorships, and if they were lucky enough, and most of them were lucky enough to actually leave before they were taken to the extermination camps. They were forced out early on. Most of them migrated to England first, came to the United States later. And these are the guys who helped build the atomic bomb.